Hello, Mr. Holmes. Continuing on our journey of learning about different character sets, and in the previous video, we finished off talking about the extended ASCII character set and the ensuing chaos that resulted from this. And this is exactly what the Unicode Consortium actually summarizes on the web page. It says that before Unicode, early character encodings also conflicted with one another. That is, two different encodings could use the same number for two different characters, or use different numbers for even the same character set. And an example of this we can draw from the extended ASCII character set. And on the screen here, we have two different code pages. One is code page for the 7, which is typically the American code page, and code page 850 would have been probably used in France. And yeah, for no particular reason, that this is showing all 256 extended ASCII characters, and you can see there is a fair degree of standardization. So up to pretty much the about halfway, the characters are all pretty much all the same. That's because remember the 7-bit ASCII character code, the standard ASCII is kind of set. But after about halfway, things start to go a bit crazy. So you can see over here, for example, next to the pound, we have a yen symbol on the American code page, whereas we have, I don't know, some sort of different symbol, and it all kind of completely changes. So exactly the same character code, the same ASCII character code, would in fact return a different symbol or different character depending on how you set up your code page. So this was an absolute mess. This created other problems as well. Any given computer, especially servers, would need to support all these different code pages, and then you furthermore still had the problem of how did you know that you were actually translating and interpreting information correctly. You know, if a French computer was talking to an American computer and you were using extended ASCII, how on earth would you know that you translated the character codes correctly, or even if you could? So this is the point of Unicode, and this is what the Unicode Consortium actually say on their webpage, and this is the goal of Unicode. Unicode provides a unique number for every character, no matter what the platform, no matter what the program, no matter what the language. So the Unicode Consortium, which is a conglomeration of all sorts of different stakeholders, including vendors from industry, big players in industry like Microsoft and IBM, and they basically said, right, enough of this now, we're going to standardize this once and for all, and we're going to create a 16-bit or a 32-bit, it's now up to 32-bit, a unique code mapping for every single character that could be ever used in any language. So that there's no need to translate anything. If you know a character's Unicode code, that's it. That's what it is. And to this end, they were quite clever in that they did the following. Right, so Unicode is a standard that provides a unique number for every character, no matter what the platform, no matter what the device or the language. It's been adopted by all the modern software providers, and now allows to be transported through many different platforms, devices, and applications without corruption. Well, that's the reason for that is pretty obvious, because we have a one-to-one mapping between the Unicode character code and the actual character that we are representing. And so let's have a look at an example of this. So in terms of how it was defined, the first thing that Unicode did is, because a great number, although not all, but a great number of computers still use or depend upon the standard ASCII code, so they kind of defined the first code page of Unicode is exactly matches that of the ASCII character set. The only difference really is that instead of us now, because we're dealing with such big indexes, we can't. It'd be because using 16-bit or 32-bit codes. That becomes you can imagine a string of 32 ones and zeros, or even 16 ones and zeros. It's just too much for our little human brains to process, and so we tend to use hexadecimal as a shorthand for that notation. So in Unicode tables, you will see the character index along the top. So it's just like we did with the binary in the standard ASCII. The tables are broken down in exactly the same way. So these numbers along the top are the high order hexadecimal codes for each column, and going down we have the trailing, or the last binary digit. So the null character over here would be Unicode 0000, whereas P over here, sorry, A over here would be Unicode 0041. Now you say, well, 41 is not A. I thought capital A was 65. Yeah, 65 in decimal. In hexadecimal, that would be represented by 41, and so it goes on. And not only do we've kept the whole backward compatibility, but also with standard ASCII, but also it allows us to create different code pages, and that are actually standardized universally now. They're not just down to what your computer has decided to use as its default code page. So in Unicode, we have a unique code for each and every single symbol is represented. You can see the Arabic characters run from the hexadecimal code 0600 to 06FFF. The Cyrillic alphabet runs from Unicode 0400 to 04FFF. And so on and so forth. Right, so hopefully that gives you an idea of what Unicode is, and how it is, how character codes have evolved into Unicode, which is now the international and universal standard for storing codes. Thanks for watching. Oh, incidentally, before we go, quick discussion as to how many codes this can actually represent. Right, so what I have up here is just Windows Calculator, and I've turned it into programmer mode so we can actually do some working out here. Right, so also a quick crash course in hexadecimal if you like. If I put it on hex and I the digits 0 to 9 are exactly as they are in normal numbers, and you can see there's the binary for 9. A is represented by 10, and you can see there's the binary value for 10. If I switch to decimal, you can see, oh, that's actually 10. So each hexadecimal code is exactly a nibble. It's 4 bits rather, half a byte. So two hexadecimal digits will be the equivalent of 255, or because we start counting from 0, that gives us 256 different character combinations we could use. If we go, if I double that, if I now go F, that you can see it's giving me that there would be 8 bits and 16 bits. That gives me the decimal equivalent of 65,535 plus the 1 for starting at 0. That gives me 65,000 characters, which is still pretty impressive. But Unicode is way up now too. So if I used the full 32 bits, that gives me well, it's a really big number. It's basically 4.2 billion different character combinations, which is way beyond what is necessary to represent anything in the world. So the numbers go, well, if we're using 32-bit Unicode, about 4.2 billion. It's well over 1.1 million characters in all languages. This is what GCC Byte Size has put on the screen on their website, but I would say it's about 4.2, 4.3 if you round it up, billion character combinations for a 32-bit code. Alright, that's it. Mr. Holmes signing out. Thanks for watching.